Time for some Shakespeare, massive or not massive, that's the question. And the story I will talk about today is about seismology on planet-hosting stars with an instrument called SUM. But before that, just quick raise of hands. Who do not call themselves an astronomer? Okay, good. So I'll tailor my talk to that. This is the periodic table for an astronomer, or at least as important. When you measure the surface temperature of a star and its luminosity, it falls in a particular or in particular regions in this diagram, which tells us a lot. The sun lives here in this diagram, and there is this diagonal where most stars fall, about 90% of stars, because stars spend 90% of their life in a phase where they will fall somewhere here. And this is basically a mass sequence. You have low mass stars here, high mass stars up there. And now the holy grail of finding planets is obviously to find Earth-like planets around sun-like stars. But to broaden our view of planet formation, we really need to look elsewhere. And so the obvious place is to look for less massive planets and more massive planets. Now, going one way here is actually easier because the stars are smaller, less massive, and they have thinner spectral lines when we take spectra. So depending on the method you use to find planets, it actually turns out to be favorable to go this way. Whereas it's harder to go the other way because the stars are larger, more massive, and the spectral lines are broad. So we are generally missing data of what kind of planet occurrence rates we have for stars that are more massive than the sun. And so a group decided to target these stars when they have retired, because all these stars here they bunch up in this region here when they become giants in basically the retirement. And so what they did was to look at a lot of giants. And so they took spectroscopy to get parameters for these stars and some models of stellar evolution in order to figure out what is the masses of these stars, and then pick those that had the right mass that would make them older versions of these stars. And what they found after they found planets around these stars was that the occurrence rates of planets were increasing when we go to more massive stars. They also found that there were fewer short, closer in planets around these heavier stars. Now, the problem is figuring out the mass of a star in this red giant region of the diagram is quite difficult because we have stars for such different masses all piling up in the same region. And we always have error bars on our observables. So when you have an error bar on that, it's hard to figure out which the true mass is when all the stars end up in the same place. And these masses for these stars were actually disputed for that same reason. And it was argued that these masses could be up to 50% lower than anticipated. And therefore, they wouldn't be older versions of what we call A stars, but they would be more like older versions of G-type stars or sun-like stars, basically. Okay, so the idea came, and that was actually Mike Island, who's sitting in this room, to just use seismology, because this time where this happened was the time where astroseismology really started to enter the game in astrophysics because of missions such as Kepler. Now, so what is astroseismology? Most stars in the sky, including the sun and the giants that I've been talking about, have convection at the surface. So this is very vigorous motion of gas. It's basically boiling at the surface. These boiling bubbles hit the surface constantly from the inside, and that excites standing sound waves that make the entire star ring. Okay? So it's basically like millions of star quakes happening all at the same time. And so that makes the star ring in natural modes, and I'm just showing some of the natural oscillation modes of the sphere. And the sun is doing that, and all these giants are doing that all at the same time.
The center of mass stays the same.
The center of mass stays the same.
It doesn't look like it.
And that is because these are overtone modes, so the interior, so you have nodes going in the radial direction. So the interior is doing the opposite of what you see at the surface. So the center of mass stays the same. Good question. Now, the most simple thing you can do with astroseismology is the only thing I have time to talk about. It's just to figure out what's the pitch of the star. So when you go to a symphony, you can listen to a violin and a cello, and you can immediately tell from the sound which one is the bigger instrument. And it turns out that the pitch of a star also depends on its physical properties. And so what I've done here, I've taken the Fourier transform of a time series of the radial velocity measurement of a star, where we basically measure how the surface is moving in and out as it's vibrating. And that frequency is the same by which the sound is ringing inside it. And so you take the Fourier transform and you see all these peaks. These are the frequencies of a whole set of oscillation modes taking place. But it has kind of a broad envelope, a frequency spectrum. You can kind of squint or smooth over this. And the dominant, or where most power comes out, is what we call nu max. That's essentially the pitch of the star. So if I change, for say, this star here by increasing its mass, this whole frequency spectrum would increase to higher frequency, okay? So our idea was to use that measurement to figure out the masses of stars. So we wanted to use the Song telescope or the Song network. That at that time it was only a single node, which was in Tenerife. And we knew from previous data that just a week of observation of such a star would give us about 10 to 20% precision on this measurement, nu max, so the pitch of the star. And so in order to give a robust conclusion on who was right on the masses of these planet-hosting stars, we needed to observe at least a handful, given the precision we had per star. And so we simply selected the most bright stars in the sky that were classified as these retired A stars, for which we had a planet found around them. Okay? This is what the data looks like for these 8 stars. And so this is the radial velocity measurement as a function of time for each of them. I've zoomed in on a few days, so you can actually see these are the oscillations taking place of the radial velocity. And so when you take the Fourier transform of each of these stars, this is the excess power coming from the oscillations, as I showed before. And so when we smooth that, we can figure out where the peak power is. That's the black dot. And that gives us the frequency, which we call nu max, which is the one we want. And of course, we want to then compare that to what we expect these stars should have in nu max, if indeed the properties that we know of them are correct. So let's say we can find the radius and the temperature and then assume the mass that the planet people say these stars have. So we basically took the temperatures that were measured for these stars, put that in there. We took the distances and brightnesses to get their radii, put it in there. And then we took the mass, the one that was disputed later, and assumed that was actually the correct mass to get a predicted nu max. And what we see is across the board, except a single star, the predicted value is basically higher than what we measure. So these dotted blue lines are larger than we measure. Okay, so why is that? So there's obviously different things going on in this relation here. One thing that could be going on is that the measurement of the temperature was systematically wrong. So if actually the temperatures of these stars were lower than we assumed, then the disagreement would go away. It would be all fine. But if you really want a temperature measurement of the surface of a star, you use interferometry. So that's basically almost what you would call a first principle measurement. And for 3 of these stars, we actually have that measurement. And there, our assumed temperatures agree within 1 sigma for all 3. So it seems that our temperatures that we used were actually fine. So that's probably not the case. Then another thing could be that the relation itself is not really working. And so you can also test that from first principle, if you like, by looking at eclipsing binaries. And again, you can use interferometry. And those tests that we have now, it seems that this relation actually holds to at least a few percent. So that can't explain the 15 to 20% discrepancy we find. But of course, when the Gaia mission, which measures distances to stars extremely accurately, comes out with data next year, that will obviously help us confirm that. And so finally, what could be wrong is simply that the assumed masses of these stars were 15 to 20% too high. And so that was the conclusion that we came up with in that paper that came out this year, that the masses of these so-called retired A stars probably were overestimated by about 15 to 20%. But same year, or not a bit later, a different result came out, which attacked the same problem, but for different stars. So these stars were measured by KATUSA. So this is a 2nd generation Kepler, so to speak. So what they found by looking at stars who had seismology from K2 and they tried to reproduce the method that the planet people use to measure mass. So they have seismic mass and say the classical spectroscopic-based mass. They find no difference. And so that seemed to be in disagreement. But let's see if we actually plot the results. So this here shows the difference in mass between what you get in the classical spectroscopic way and then seismology. And indeed, their stars, they are close to the zero line. So this is perfect agreement between the two methods. But now what happens when you plot our results on top? That's this. So what you see is the stars that we looked at were generally more massive. And the only one where we had agreement was actually a low mass star. So it is quite tempting to draw a line like this and say the discrepancy between the two methods only occur for more massive stars. In fact, those that you would call retired A stars. Whereas these ones are more solar mass stars, they actually agree. Okay, why do we think that is occurring? There's probably not a coincidence, but this mass transition below which the agreement is good, above it's not, is also the mass transition in this astroseismic HI diagram that I showed in the very beginning. Stars in this region, they move relatively slow if they are below that mass threshold, but just above it, they move extremely quickly. And so if you have a if you have a star in this region, you have its temperature and luminosity with some error bar that covers both regions that have high mass stars moving through here very quickly and those moving slow. If you don't take that difference in speed into account, you're basically overestimating your masses. In the future, we'll get tests, which gives us even more data to check this on, whether we are right on this interpretation. And so I'll just leave my summary up here and say we're looking forward for both Gaia and tests for next year. Thank you.